In elementary algebra, the binomial theorem describes the algebraic expansion of powers of a binomial. According to the theorem, it is possible to expand the power n into a sum involving terms of the former x, b, y, c, where the exponents b and c are non-negative integers with b plus c equals n, and the coefficient of each term is a specific positive integer depending on n and b. For example, the coefficient a in the term of her x, b, y, c is known as the binomial coefficient for. These coefficients for varying n and b can be arranged to form Pascal's triangle. These numbers also arise in combinatorics, where gives the number of different combinations of b elements that can be chosen from an n-element set. History. Special cases of the binomial theorem were known from ancient times. The 4th century BC, Greek mathematician Euclid mentioned the special case of the binomial theorem for exponent 2. There is evidence that the binomial theorem for cubes was known by the 6th century in India. Binomial coefficients, as combinatorial quantities expressing the number of ways of selecting k objects out of n without replacement, were of interest to the ancient Hindus. The earliest known reference to this combinatorial problem is the Chandasastra by the Hindu lyricist Pingala, which contains a method for its solution. The commentator Haliada from the 10th century AD explains this method using what is now known as Pascal's triangle. By the 6th century AD, the Hindu mathematicians probably knew how to express this as a quotient, and a clear statement of this rule can be found in the 12th century text Lilavati by Bhaskara. The binomial theorem as such can be found in the work of 11th century Persian mathematician Al-Khariji, who described the triangular pattern of the binomial coefficients. He also provided a mathematical proof of both the binomial theorem and Pascal's triangle, using a primitive form of mathematical induction. The Persian poet and mathematician Omar Khayyam was probably familiar with the formula to higher orders, although many of his mathematical works are lost. The binomial expansions of small degrees were known in the 13th century mathematical works of Yang Hui and also Chu Shixia. Yang Hui attributes the method to a much earlier 11th century text of Jia Jian, although those writings are now also lost. In 1544, Michael Stiefel introduced the term binomial coefficient, and showed how to use them to express in terms of via Pascal's triangle. Blaise Pascal studied the eponymous triangle comprehensively in the treatise Traité du triangle arithmétique. However, the pattern of numbers was already known to the European mathematicians of the late Renaissance, including Stiefel, Niccolò Fontana Tartaglia, and Simon Stevin. Isaac Newton is generally credited with the generalized binomial theorem, valid for any rational exponent. Statement of the theorem. According to the theorem, it is possible to expand any power of x plus y into a sum of the form where each is a specific positive integer known as a binomial coefficient. This formula is also referred to as the binomial formula or the binomial identity. Using summation notation, it can be written as the final expression follows from the previous one by the symmetry of x and y in the first expression, and by comparison it follows that the sequence of binomial coefficients in the formula is symmetrical. A simple variant of the binomial formula is obtained by substituting 1 for y, so that it involves only a single variable. In this form, the formula reads or equivalently examples. The most basic example of the binomial theorem is the formula for the square of x plus y. The binomial coefficients 1, 2, 1 appearing in this expansion correspond to the second row of Pascal's triangle. The coefficients of higher powers of x plus y correspond to later rows of the triangle. Notice that the powers of x go down until it reaches 0. The powers of y go up from 0. The nth row of the Pascal's triangle will be the coefficients of the expanded binomial. For each line, the number of products is equal to For each line, the number of product groups is equal to. The binomial theorem can be applied to the powers of any binomial. For example, for a binomial involving subtraction, the theorem can be applied as long as the opposite of the second term is used. This has the effect of changing the sign of every other term in the expansion. Geometric explanation for positive values of a and b. The binomial theorem with n equals 2 is the geometrically evident fact that a square of side a plus b can be cut into a square of side a square of side b, and two rectangles with sides a and b. With n equals 3, the theorem states that a cube of side a plus b can be cut into a cube of side a cube of side b, 3a times a times b rectangular boxes, and 3a times b rectangular boxes. In calculus, this picture also gives a geometric proof of the derivative if one sets and interpreting b as an infinitesimal change in a. Then this picture shows the infinitesimal change in the volume of an n-dimensional hypercube, where the coefficient of the linear term is the area of the n faces, each of dimension. Substituting this into the definition of the derivative via a difference quotient and taking limits means that the higher order terms, and higher, become negligible, and a yields the formula interpreted as the infinitesimal change in volume of an n-cube. A side length varies as the area of n of its dimensional faces. If one integrates this picture, which corresponds to applying the fundamental theorem of calculus, one obtains Cavalieri's quadrature formula. The integral. See proof of Cavalieri's quadrature formula for details. The binomial coefficients. The coefficients that appear in the binomial expansion are called binomial coefficients. These are usually written and pronounced n. Choose k. Formally, the coefficient of xn minus kyk is given by the formula, which is defined in terms of the factorial function n. Equivalently, this formula can be written with k factors in both the numerator and denominator of the fraction. Note that, although this formula involves a fraction, the binomial coefficient is actually an integer. Combinatorial interpretation. The binomial coefficient can be interpreted as the number of ways to choose k elements from an n-element set. This is related to binomials for the following reason. If we write n as a product n, according to the distributive law, there will be one term in the expansion for each choice of either x or y from each of the binomials of the product. For example, there will only be one term xn, corresponding to choosing x from each binomial. However, there will be several terms of the form xn minus 2y2, one for each way of choosing exactly two binomials to contribute a y. Therefore, after combining like terms, the coefficient of xn minus 2y2 will be equal to the number of ways to choose exactly two elements from an n-element set. Proofs. Combinatorial proof. Example: the coefficient of xy2 in equals because there are three x, y strings of length 3 with exactly two y's, namely, corresponding to the three two-element subsets of 1, 2, 3, namely, where each subset specifies the positions of the y in a corresponding string. General case expanding n yields the sum of the two n products of the form e1 e2 en where each ei is x or y. Rearranging factors shows that each product equals xn minus kyk for some k between 0 and n. For a given k, the following are proved equal in succession: the number of copies of xn minus kyk in the expansion, the number of n character x, y strings having y in exactly k positions, the number of k element subsets of 1, 2, n. This proves the binomial theorem. Inductive proof. Induction yields another proof of the binomial theorem. When n equals 0, both sides equal 1, since x0 equals 1 n. Now suppose that the equality holds for a given n. We will prove it for n plus 1. For j, k0, let f, j, k denote the coefficient of x, j, y, k in the polynomial f. By the inductive hypothesis, n is a polynomial in x and y such that n, j, k is if j plus k equals n, and 0 otherwise. The identity shows that n plus 1 also is a polynomial in x and y, and since if j plus k equals n plus 1, then plus k equals n and j plus equals n. Now, the right-hand side is by Pascal's identity. On the other hand, if j plus kn plus 1, then plus kn and j plus n, so we get 0 plus 0 equals 0. Thus, which is the inductive hypothesis with n plus 1 substituted for n, and so completes the inductive step. Generalizations. Newton's generalized binomial theorem around 1665. Isaac Newton generalized the formula to allow real exponents other than non-negative integers. In addition, the formula can be generalized to complex exponents. In this generalization, the finite sum is replaced by an infinite series. In order to do this, one needs to give meaning to binomial coefficients with an arbitrary upper index, which cannot be done using the above formula with factorials. However, factoring out from numerator and denominator in that formula, and replacing n by r, which now stands for an arbitrary number, one can define where is the Pochhammer symbol here standing for a falling factorial. Then, if x and y are real numbers with x greater than y, and r is any complex number one has when r is a non-negative integer, the binomial coefficients for k greater than r are 0, so specializes to, and there are at most r plus 1 non-zero terms. For other values of r, the series has infinitely many non-zero terms, at least if x and y are non-zero. This is important when one is working with infinite series and would like to represent him in terms of generalized hypergeometric functions. For example, with r equals 1/2 gives the following series for the square root. Taking the generalized binomial series gives the geometric series formula, valid for, more generally, with r equals -s. So, for instance, when generalization's formula can be generalized to the case where x and y are complex numbers. For this version, one should assume x greater than y, and define the powers of x plus y and x using a holomorphic branch of log defined on an open disk of radius x, centered at x. Formula is valid also for elements x and y of a Banach algebra as long as xy equals yx, x is invertible, and y, x, less than 1. The multinomial theorem. The binomial theorem can be generalized to include powers of sums with more than 2 terms. The coefficients are known as multinomial coefficients, and can be computed by the formula combinatorially. The multinomial coefficient counts the number of different ways to partition an n-element set into disjoint subsets of sizes k1, km. The multibinomial theorem. It is often useful when working in more dimensions, to deal with products of binomial expressions. By the binomial theorem, this is equal to this may be written more concisely, by multi-index notation, as applications. Multiple angle identities for the complex numbers. The binomial theorem can be combined with de Moivre's formula to yield multiple angle formulas for the sine and cosine. According to de Moivre's formula, using the binomial theorem, the expression on the right can be expanded, and then the real and imaginary parts can be taken to yield formulas for cos and sin. For example, since de Moivre's formula tells us that which are the usual double angle identities. Similarly, since de Moivre's formula yields in general and series for either number E is often defined by the formula, applying the binomial theorem to this expression yields the usual infinite series for E. In particular, the kth term of this sum is as n infinity. The rational expression on the right approaches 1, and therefore this indicates that E can be written as a series. Indeed, since each term of the binomial expansion is an increasing function of n, it follows from the monotone convergence theorem for series that the sum of this infinite series is equal to E. derivative of the power function. In finding the derivative of the power function f equals xn for integer and using the definition of derivative, one must expand the binomial nth derivative of a product to indicate the formula for the derivative of order n of the product of two functions. The formula of the binomial theorem is used symbolically. The binomial theorem in abstract algebra formula is valid more generally for any elements x and y of a semi-ring satisfying xy equals yx. The theorem is true even more generally. Alternativity suffices in place of associativity. The binomial theorem can be stated by saying that the polynomial sequence 1, x, x2, x3 is of binomial type. In popular culture, the binomial theorem is mentioned in the Major General's song in the comic opera The Pirates of Penzance. Professor Moriarty is described by Sherlock Holmes as having written a treatise on the binomial theorem. The Portuguese poet Fernando Pessoa, using the heteronym Álvaro de Campos, wrote that Newton's binomial is as beautiful as the Venus de Milo. The truth is that few people notice it.